Welcome to the 6th lecture of my series on the Holy Trinity of vector calculus. This particular lecture is going to be a short one because it has a very small agenda. The agenda of providing an alternate proof of a very important theorem. Note that we have already met all the major members of the Holy Trinity, the gradient, the divergence, and the curl. We have been spending the last couple of lectures talking about the third of these, the curl. In the previous lectures, we had introduced the curl as effectively the surface density of circulation in planar loops. And turning this definition on its head, we had proven a very, very important theorem. Stokes' theorem, which tells us that the line integral of a vector field over the boundary gamma of a surface sigma is actually equal to the surface integral of curl of A dot n hat ds or curl of A dot ds vector over the surface sigma. Now the proof that we gave there was basically a geometrical one which essentially hinges on the definition of the curl. Now we had also seen that at least in Cartesian coordinates, we can rewrite curl in such a way that it turns out to be nabla operator crossed with the vector field A. And this is a very convenient form in which we can carry out all the calculations. Now this nabla operator cross A form of the curl gives us an alternative way of proving Stokes' theorem. This actually is a more calculus-y kind of proof, a proof which uses more algebra, more calculation, and it is also one that is more commonly found in textbooks. When I first thought about talking about the curl and Stokes' theorem, I had thought that I would omit this particular proof. Firstly, because I personally prefer the geometrical one that we had done earlier a bit more, and also because this proof can be found in most textbooks. It turns out, however, that this alternate proof is also quite useful. This more formal proof can give you some practice in understanding some things that we had already discussed before, like how to connect a surface integral to a double integral, and so on. Also, you are more likely to find this alternate proof in textbooks, as I have said, and so if you are following a textbook, this might be a good thing to learn. Now the formal proof of Stokes' theorem is slightly involved. So we will break this up into steps. We will first prove a result which is essentially Stokes' theorem but in the special case of a two-dimensional world. This is called Green's theorem in a plane. And the theorem essentially goes this way, that if you have a line integral over a curve C, a flat curve C, which bounds a region D, of this differential m dx plus n dy, where capital M and capital N are both functions of x and y, then this line integral is the same as the double integral over dx dy of this quantity del n del y minus del m del x. If this reminds you of a component of the curl, you would not be too far out. In fact, if we essentially took a situation where we had a vector A which had only two components, mi and nj, then A dot dl would of course be m dx plus n dy, and in this case the curl of A would have only one non-zero component, which is del n del y minus del m del x. Here, of course, I am assuming that m and n are functions of x and y only. There is no z involved here. So, this theorem can be thought of as a special case of Stokes' theorem applied to the two-dimensional world. The reason why it has a separate name is, of course, it's A, something which was discovered before Stokes' theorem by Green, and B, because it is actually used as an ingredient in the proof of Stokes' theorem. So, even though this is a special case, it has to be established as an independent result first. Now, I'm going to give a proof of Green's theorem now, but I'm going to prove it for a rather simple kind of curve. In fact, it is called a simple curve. Here the idea is that the curve is such that a line parallel to the x-axis, a line shown by dotted orange line here, will cut this curve at a maximum of 2 points. Of course, if the line is drawn up here, it will not cut the curve at all. Or in special cases like this and this line, they will touch the curve at only 1 point, but the maximum number of intersections will be 2. And that is the simplest possibility for closed curves. Now, this will happen not only for lines parallel to the x-axis, this will also happen for lines parallel to the y-axis, like the purple vertical line here. It will cut the curve, if at all, at a maximum of 2 points. Now, for such a curve, we can do the following. First of all, let's look at one of the two terms in my double integral del n del x dx dy. Note that because a line parallel to the x-axis cuts this curve at most 2 points, but it does cut it at more than 1 point, you cannot describe this entire curve by expressing x as a particular function of y. After all, a function of y will have only one value for a given value of y. Here, in order to describe the curve, you need two values. So you need two functions. Over this red piece of the curve, x will be described by f1 of y. This is the part which I am calling c1. Over the other piece, c2, x is again described by a single well-defined value of y, f2 of y. And of course, these two curves together form the curve C, the closed curve C, and y1 and y2 are the bounding values of y, beyond which, of course, a horizontal line will not cut the curve at all. Now, this double integral can be thought of as a repeated integral. You first do an integral over either x or y. In this case, let's choose to do the x integral first. So, for a given value of y, say this value, x will go from this value, which is f2 of y, to this value, which is f1 of y. So, del n del x, the integrand, has to be integrated over x from f2 of y to f1 of y. And once this integral is done, that is, your integral over this green strip is completed, the strip is moved to this entire region, which means now y has to change from y1 all the way up to y2. Of course, for each value of y, say when y is here, the x limits are dictated by that particular value. So here it's going to be f2 for this particular value of y to f1 for this particular value of y, and so on. Now, the reason why we chose to do the x integral first is rather obvious. Remember, when we are doing this integral, y is treated as a constant and only x is being integrated over. So, although this is a partial derivative del n del x, this essentially behaves like a total derivative as far as this integral is concerned. So, this is nothing but the differential of n. So, when you integrate that, you just get n at the end of the interval with n at the beginning of the interval. The end of the integral is given by x being f1 of y, and the beginning is given by x being f2 of y. So, this integral, which is only half the work done, has to be n with f1y replacing x and y as arguments, minus n f2y comma y coming from the lower limit. So, this is what this integral is, and now it becomes an integral over just y. But now, notice that I can break this up into two pieces. The first one is obvious, n f1y comma y dy integrated from y1 to y2. So, integrate from y1 to y2 but with x being replaced by f1 of y, which means you are actually going in this direction along the curve C1. So this integral, the part written in red, is nothing but n dy integrated along C1. What about the other part? The minus sign here is taken care of simply by switching the integration limits. The limits were y1 to y2, now they have become y2 to y1. And here x has been replaced by f2 of y. But notice that this is exactly what you do when you integrate n dy along this curve C2. You go from y2 being the value of y to y1 being the value of y at the end, and over this curve the argument x for n has to be replaced by the value of x which is pertinent to this curve, which is x is f2 of y. So this piece is nothing but n dy integrated over C2. So this whole thing becomes a closed integral over C1 first and then C2. That is the integral over C. I must stress one thing which I may have omitted a while ago. In the case of a two-dimensional double integral, the kind that we are using Green's theorem on, the traversal direction for the loop is always taken to be counterclockwise. So which is why here C is being traversed in a particular direction, and that dictates that over C1, y changes from y1 to y2, whereas over C2, the other part of the curve, y changes from y2 to y1. So what we have established is that the double integral of del n del x over the region D is actually the same as the line integral of n dy over the curve C bounding that region, the line integral being taken by traversing the curve in the counterclockwise direction. Now, a very similar treatment can be done for the other part, minus del m del y dx dy. Here, we are once again going to use the fact that we have a simple curve to essentially carry out the y integral first, but for each y integration, the value of y will go from a lower value, which is fixed by the given value of x, to an upper value. So from g2x to g1x, as you can see. And once this integral over the strip is completed, the strip is moved so that this entire region is covered. And for that, x needs to change from x1 to x2. So the integral, double integral of del m del y minus del m del y essentially becomes this. And once again, this integral can be carried out trivially just by replacing y in m by g1x for the upper limit and g2x for the lower limit. And because you have a minus sign here, I have switched the two limits, and you end up with m x comma g2x with a plus sign and mx comma g1x with a minus sign. Once again, note that I should have really got the negative of this, but there's a minus sign here. And that takes care of this change of sign. Now let's break this up into two pieces once again. The first piece, of course, is mx comma g2x dx integrated from x1 to x2. That's simply nothing but this particular line integral being carried out of m dx. Note that here x does go from x1 to x2, the limits given here. And on this curve, y is given by g2x. So that's what we have put in here. What about the other piece? Once again, what we have to do is get rid of the minus sign by switching the limits of the integral. x1 to x2 becomes x2 to x1. And you go from x2 to x1, but you go in such a way that y is replaced by g1x. That is, you are going along the curve C1 here. So this piece gives you the integral over C2, and this piece gives you the integral of m dx over C1. And the two together definitely gives you the integral of m dx over the closed contour C. So adding these two results together, what we get is the integral over the closed contour C, the boundary of an area D traversed in a counterclockwise direction of m dx plus n dy is given by the double integral carried out over the region D of del n del x minus del m del y. Now, of course, this proof was only for simple curves where lines parallel to the axis cut the curve at most at 2 points, which is why for both parts of the proof, we could divide the curve into 2 pieces and just use 2 functions. Now what if we had more complicated curves? Say a curve like this, which bends into itself, so that a line parallel to the y-axis cuts it in more than 2 points. In this particular example, this particular blue line cuts it at 4 points. Now one way to tackle this would be actually to use 4 different functions for y as a function of x and carry out the same kind of argument. Another way would be to simply change this region into 2 simple curves. If you join these 2 points by a line like this, it's easy to see that you can actually split up this line integral into a line integral over this outer line minus a line integral over this inner line. Both carried out counterclockwise. But of course, when you're subtracting these two, in the overall subtraction, these 2 pieces will just cancel out, these 2 extra pieces. And this curve, which was the green curve, which was being traversed counterclockwise, when you subtract, it will give you contributions in this direction, which means you are essentially going to get this contribution, which is of course the contribution for this curve. And since Green's theorem works for both the purple curve and the green curve, because both of them are simple curves, it also works for the difference. In this way, you can extend this proof to any non-simple curve whatsoever, as long as the curve is closed. The line integral of m dx plus n dy evaluated over any non-simple curve or simple curve traversed counterclockwise is the double integral of del n del x minus del m del y evaluated over the region bounded by the curve. Now that we have Green's theorem in a plane under our belt, we are going to use this to prove Stokes' theorem. And for that, what we are going to do is we are going to use the standard trick of changing a surface integral into a double integral, which we discussed in my 3rd lecture. Let us consider, at least to make a beginning, a surface sigma which is a simple surface. Simple in the sense that if you draw a vertical line up from the xy plane, this line cuts the surface at 1 point at the most. Of course, there are vertical lines which can draw from the plane which don't cut the surface at all, but all other lines which do cut the surface at only 1 point. And that means that here the value of z on this surface is uniquely given by a function of x and y, because there's only one z value, 1 point where this intersection occurs. So the surface sigma can be defined simply by this equation, z minus f of xy equals 0. Now because we are going to ultimately relate the line integral of a dot dl over the boundary gamma of this surface sigma to the surface integral of curl of a dot ds, one thing is very important. We need to figure out what the normal to this surface is so that we can figure out what ds vector is going to be. The normal to this surface is of course going to be in the direction given by the gradient of this function whose constancy defines the surface. I am writing n vector here instead of n hat because we have not bothered to normalize this. I've just calculated the gradient. The length of this vector, of course, is whatever the length the gradient has. And if you remember our discussion on the conversion of a surface integral into a double integral, you don't really have to bother dealing with unit normals because the normal occurs twice, once in the numerator of the expression, once in the denominator, dotted with k hat, and it will just cancel out. Any normalization factor would just cancel out. So n vector here is simply given by this gradient, which is minus del f del x I hat, which I have just shortened as fx, minus del f del y j hat plus 1, which is del z of this z, times k hat. So n vector dot k hat, which is going to go into the denominator of the corresponding double integral, is simply going to be 1. Now let us leave that aside for the time being and return to the question of the line integral of A dot dl over the closed curve gamma bounding the surface sigma. A dot dl's line integral, of course, is nothing but ax dx plus ay dy plus az dz's line integral over the curve gamma. And let's try this out in a bit more detail. Note that over the curve gamma, the z is also given by the same function f of xy. Of course, the xy points have to be taken not from any arbitrary point on the plane, but from the boundary C of this projection D of the surface sigma. So, sigma has been projected down to produce a region, a flat region D, and C is the boundary of that region. And as you traverse the boundary of the region, at every point above this boundary, there is a point on the boundary, gamma of sigma. And this point on the boundary is simply given by the same coordinates x and y, with z being given by f of xy. So the line integral over gamma can be converted into a integral over c, where what we have to remember is z has to be replaced by f of xy. It's easy to do over the first two terms. All you have to do is replace the z, the third argument of ax and ay respectively, by f of xy in the two cases. A third piece, az dz, takes a bit more work, simply because here az depends on z, so that there the replacement of z by f of xy has to be done. But also you have to realize that you have dz, the change in z, as you move along this curve. So as you move along this curve, of course, x and y changes. Z changes because z is a function of x and y. So change in z dz is given by del z del x dx plus del z del y dy. Del z del x is the same as del f del x, z being f of xy. And of course use the abbreviation fx for that. So fx dx plus fy dy, this is nothing but dz. So this is what we do in order to convert this line integral of a dot dl over the closed loop gamma, which was not necessarily a flat loop, into the integral over this flat planar loop C in the xy plane. Now it's easy to see that we can collect the dx and dy terms in this whole expression together to rewrite this as the line integral over C of ax plus az times fx times dx, of course, plus ay plus az fy times dy. In all of this, of course, wherever z appears as an argument in either ax, ay or az, I have to replace that by f of xy. So this is of the form m dx plus n dy, where m is a function of xy given explicitly by ax with arguments x, y and f of xy, plus az with arguments x, y, f of xy times del f del x, what we have shortened to fx here. And n xy, this coefficient is simply given by ay with arguments x, y, f of xy, plus az with arguments x, y, f of xy times the derivative del f del y. Now I'm being a bit explicit about every argument. Maybe that's a bit boring to hear, but it's going to be very important in what follows. Because in what follows, what we need to do is convert this line integral into a double integral using Green's theorem. And for that, we need the derivatives del m del y and del n del x. And in order to calculate them, we have to worry about the fact that m, for example, depends on y not only because there is an explicit y sitting here and here, it depends on y also through the f of xy term. So it's very important to keep track of all the dependencies. So let's see. del m del y, if you were to calculate that from here, you would get two terms from the differentiation of ax. One, the direct one, which comes in simply as del ax del y. After all, ax depends on y directly through the second argument. But it also depends on y through the third argument z. So you have to do del ax del z, but multiply that by the rate at which f changes with y, del f del y. This is nothing but the chain rule of partial derivatives being used. These two terms in purple come from this first term here. The terms in orange actually comes from this second term. The second term, of course, is a product of az and fx. So you have one term in which you are going to do del y on fx, leaving az intact. And I have just explicitly written that as az times del 2f del y del x. You get two more terms by differentiating just this one while leaving this intact. One of them, just like del ax del y, from this I get del az del y. Of course, that's multiplied by fx, del f del x overall. And another term that I get is one I get when I multiply del f del x by the derivative term I get from the fact that az depends on y also through this argument. So del az del z times del f del y, of course multiplied overall by del f del x. So this is the overall derivative that I get when I calculate del m del y. Looks quite complicated if you were to see the whole expression, but actually it's rather straightforward. You just have to remember that the functions here depend on x and y not only through the explicit dependencies as written, but also through the fact that z will depend on x and y. After all, you're doing the integral really over gamma, where z is f of xy, not really over c. I'm converting it into an integral over c, but the actual integral is over gamma. So over c, of course, z is 0. But on gamma, z was given by f of xy. That's what we have to bear in mind. What about del m del x? A very similar calculation will give you del ay del x plus del ay del z del f del x. And these are the two terms which come from the first piece here. Three terms will come from here. One, when you differentiate this with respect to x, so del 2f del x del y times az. And two more terms. One, which comes from del az del x times del f del y. And the other term which comes from del az del z del f del x times del f del y. What we need to do is subtract the two. Del n del x minus del m del y is the integrand in the double integral that we need to calculate. And when you do that, the result is pretty straightforward. These two pieces cancel out because mixed partial derivatives are equal, and these two pieces also cancel out simply because they are the same terms. Now you have 6 terms left over still, and these 6 terms can be grouped into simple pieces. One which has no partial derivative of f multiplying it, that is del a y del x. Remember, we are doing del n del x minus del m del y. Del a y del x minus del a x del y, that's this piece. Then two more pieces which have del f del y in them, that is these two. So you get del az del x minus del ax del z. And one more piece, one more pair rather, which have del f del x multiplying both terms, and that's del ay del z minus del az del y. Now these pieces here should begin to look very, very familiar. They are of course directly related with components of the curl. In fact, this is the curl of a z component. This one is almost the y component, but in the y component you have del ax del z minus del az del x. So this is minus curl of a's y component times del f del y. This is again minus curl of a's x component times del f del x. But the minus signs are all good. Remember, my n vector that we had worked out before was actually minus del f del x I hat minus del f del y j hat plus k hat. This was the vector which is in the direction of the normal to the surface sigma. So this expression that we have is nothing but n vector dotted with curl of A. So line integral of A dot dl over the line gamma, which is simply m dx plus n dy in our new abbreviation that we have introduced, is equal to the double integral del n del x minus del m del y dx dy is integral over d, where C is of course the boundary of D, and this gamma is the boundary of sigma, and D is nothing but the projection of sigma. So this is the double integral over D of this quantity which we have just established as curl of A dot n hat, where the values of Z have to be put in as f of xy. So this thing is being evaluated really on the surface sigma, where Z is given by f of xy, multiplied by dx dy by this factor, which happens to be 1. Remember, n has just 1 as the Z component. So the reason why I brought this in is that this is the factor which actually corrects for the fact that on the surface, the pieces that you have of sigma are slanted in comparison with the xy plane. So the projected areas are actually different. Here, if it actually used a unit normal n hat, this would have really been the cosine of the angle between the piece up there and the projection in the xy plane. Here, of course, this factor is simply 1. The 1 by cosine theta factor which should have been there is actually hidden in this n vector on the top. In any case, instead of using n hat in both the numerator and the denominator, you can also use n vector. Now, as we discussed in some detail in the third lecture of this series, this whole construction is nothing but a way of evaluating the surface integral of curl of A dot ds over the surface sigma by projecting it onto the xy plane first. So what we have ultimately obtained is that the line integral of A dot dl over a closed curve gamma, which is the boundary of a surface sigma, is nothing but equal to the surface integral of curl of A dot ds over the surface sigma, which of course is Stokes' theorem. Now the proof that we have given here has limitations. Limitations in the sense that we have assumed that the surface used is simple, not a surface like this one which bends over itself, so that you cannot describe it by saying that z is a given fixed function of x and y. But the extension of the proofs to such non-simple systems is pretty straightforward. In this case, you would have to sort of break up the surface into two pieces, each of which would be simple surfaces, and Stokes' theorem would work for each one of them, so it would work for the combined one as well. I'm not going to bother giving you the most general proof in this case, because I'm pretty sure you can think of how to repair the proof in case your surface were even more weird, like something like this, and so on. The upshot of all this is, as long as you have a closed curve bounding any surface, we have proven the Stokes' theorem, that is the line integral of A over the closed boundary gamma has to be equal to the surface integral of curl of A, or the flux of curl of A. To summarize, we have given two different proofs of Stokes' theorem so far. The first one used the basic idea that the projection of curl of A in a given direction is the surface density of the circulation in a plane normal to that direction. And the second proof was based on a more algebraic idea that curl of A has components which are given by the cross product, so to speak, of the nabla operator with A. We then went on to use Green's theorem, basic calculus, and connection between double integrals and surface integrals and so on to establish Stokes' theorem from there. At this point, we have met all the three major players in our story: the curl, the grad, and the divergence. We have also been introduced to the two major integral theorems that play a huge role in mathematical physics, namely Gauss' theorem and Stokes' theorem. This does not mean that all that we had to say about grad, div, and curl has been said. After all, there are situations where you use these operators in tandem, do multiple applications of these operators on certain things, or where you apply one of these operators on products or sums. These and many other issues are still to be discussed, but for that you will have to wait for later lectures. Bye for today.